Okay, good morning. Let's start. I assume that some other people will join us like in 5 or 10 minutes. Or we already reached the actual group of people who will attend the lecture, but usually in the first week there are like double the amount of people and then it drops out to this kind of thing. Yeah, so this is statistical methods, a course that will now not run for 2 weeks and then be done, but will run for the entire winter term and then for the summer term. And of course the plan today is then first to give you an introduction to the course, so to know that, to make sure that you know what's going on. And yeah, and then also start with some content with respect to the overall course layout, specifically in the winter term. So the idea of the entire course is to refresh your statistics knowledge from undergrad statistics using what is known as the general linear model in the winter term. Yeah, often it turns out that it's more or less all novel and there's not much of a refreshment going on. The idea is then, in addition, to make you familiar with common data analytical procedures in functional neuroimaging. And as I also said for the neurocognitive methods course, the focus is on the theory, because as I mentioned there will never be a time again where it's really appreciated that you learn the theory. This is also something important. So when I said you actually will not learn the theory later on, this also has to do with the fact that often you are in labs that don't really appreciate theoretical development, or definitely nobody. So you don't get kind of in kind of working environments. It's basically assumed that you know theory or not. That's always a little bit unclear. But definitely you will not get any benefits from saying, oh, I think I have to study for half a year and I will not produce anything. So really now is the time to learn the theory, get into it and build a solid foundation so that you can get into other theoretical aspects of data analysis later on much easier, because you already established some good foundations. And yeah, this course is meant to help you with that. So that's the very general idea. And because it's focused on the theory, we will basically today see a little bit of what doing what we'll discuss means in practice, but after that we will mainly talk about things in abstract and mathematical and theoretical ways. Yeah, with respect to the course outline, this course actually has 3 sections and 3 corresponding exams, but more about the exams in a second. So an important first aspect of this is that you revise your high school / undergraduate mathematics. And this are these mathematical preliminaries, which consists of these 6 sections, sets and functions, which establish there's a lot of notation. It's nothing of this is hard, it's just things that you need to know. Calculus, which especially for German students will be the stuff that they learned in school, maybe not partial derivatives, but that's fairly easy if you understand what a normal derivative is. Probabilistic foundations is some basic knowledge about probability distributions, essentially that probabilities sum to 1 and that you can have probability distributions with more than one variable. Gaussian distributions is something that all psychologists will have seen many times. That's just a bell-shaped curve. The most important thing for the winter term and getting into formulating the GLM is this matrix algebra stuff, which is pretty short, and for anyone who has taken undergraduate mathematics at university, that would be familiar. I don't know what's going on with teaching matrix algebra in high school these days. I don't think it's happening more than it used to happen when I was young. Yeah, get into that. So that's mathematical preliminaries that's left for your self-study. You can also So there are different ways to work on this material. So one way is to just sit down this week and work through it. The other thing is that you confuse yourself from what is happening here. So for example, that we formulate things in matrix form, and then basically based on what we're currently dealing with, look into these foundational aspects. So yeah, either one is fine. Actually, you will I give you hints and remarks when certain things might confuse you. Then it makes sense to look into these mathematical preliminaries, because that's always the thing with mathematical preliminaries. You either work on them first, then you don't know really why you're doing this, or you work on them while you are exposed to other content, then you know why you're doing it, but maybe not doing it as then you know why you're doing it. So yeah, basically it's a question for yourself. The thing that I'm always referring to with this mathematical preliminaries are in the script, these first 80 pages, I think. Yeah, it's, as you see, there's not much to calculate or something. Well, a little bit of derivatives and so on, but the most of this is actually notation and understanding the common mathematical notation. So just work through it. It's fairly short. If you feel you don't fully get something, Google it, read the Wikipedia entry. There are also what I call bibliographic remarks. So there are some references if you really want to learn more. For example, about calculus, then the Spivak book is a good undergraduate book on calculus. Yeah. So that's the mathematical preliminaries. There's also YouTube playlist on this by me. I think it has most of the stuff. I think it doesn't really have a calculus section, because somehow this was never recorded. But matrix algebra it has, so you can definitely watch those videos. And it has the probabilistic foundation, so you can definitely watch those. If you feel that in addition to the text, you need me trying to speak English and finding the words and so on. Yeah, so that's the mathematical preliminaries. So this is important for basically everything that you will do in terms of data analysis. This is important for the winter term. This is also important for the summer term. And it's also actually important for what you will do in programming, because matrices will be a very important component of doing programming. So look into it. The reason why, so yeah. Sometimes in the past, so just that you know how this mathematical preliminaries comes about. Sometimes in the past I did in the week before the term I did this mathematical pre-course, and this is now basically still existing, but it's existing in the virtual world of YouTube lectures and this material. So we don't do this pre-course anymore right now. Maybe at one point I do it again. Yeah, get into it. And it's not only, and this I want to emphasize, it's not only there for the foundation so that you understand the other stuff, but it also will form 1/3 of the exam. Yeah, but let's get back to the exams later. The second big part, which we then start today, is Glm Based Fmri, which essentially yields these blobs on the brain that you should have seen, and you will definitely see more in cognitive neuroscience, in your cognitive neuroscience courses, A and B, and also I guess social and affective neuroscience. And it's kind of a basic way of analyzing data, but the good thing is that it allows us to introduce a lot of stuff that is fairly general in terms of the general idea of modeling data and then estimating parameters and then doing some interpretation or evaluation of the model, and it will allow us to introduce more general concepts like maximum likelihood estimation or statistical testing. So what really is a statistical test? It also has certain aspects that are specific to fMRI data. So you also get some expertise in the imaging domain that you will not hear in, or that you will also not find in general statistics books. So in general statistics books, you might find an introduction to general linear models. But certain things that are particularly to brain imaging, where the general linear model is essentially applied to time series data, which it was not originally built for, but can be used for, and actually not only time series, but also spatially ordered data. So basically the GLM is used to analyze spatial temporal data and can be viewed, if you went through the whole thing here, actually as a computational simplification of estimating parameters of a big spatial temporal model of how bold data over space and time evolves. So these aspects, they will feature in things like covariance, component estimation, restricted maximum likelihood estimation, and specifically this random field theory based inference, which we will do in the end. So these parts relate a little bit more to the temporal aspects, so estimating covariance components, and the last part a little bit more to the spatial aspects relating to random field theory, random field theory and spatial aspects. So the bottom line of this fMRI GLM analysis is that on the one hand, that's kind of how fMRI data has been analyzed since the early 90s. And it may be somewhat surprising that this kind of data analysis is still done. However, or that this is still something to know about. However, it's also, it's weird how these things go, but for example, over the last couple of years, there was some discussion about the reproducibility of neuroimaging results, and the question of do we use large enough sample sizes and so on, and questions of how to do, for example, power calculations when dealing with these kind of tests are only currently being employed. So you will, it depends on with whom you talk. So some people who might be a little bit in their little domain in cognitive neuroscience might think that GLM-based fMRI is old school because nowadays we use pattern classifiers. They are a little bit misled because there's still a lot of GLM-based fMRI going on, and there are actually current questions about GLM-based fMRI that only now start to be explored. So it's on the one hand, it's kind of traditional classical inference, frequentist, and mainly established in the 90s. On the other hand, it's also still, there's still ongoing research in these aspects, and some people are still developing this framework. So that's the winter term. And I think the fundamental thing about why talking about the GLM is important, because it's such a well understood model that allows to really show how probabilistic modeling for data analysis works. So that's, and if you understood how the GLM is applied in fMRI, then it's actually much easier to incorporate other things that happen in statistical modeling. So this is the second part, and then the third part of statistical methods will happen in the summer term. And in the summer term, I frequently skip around what we are doing, because there are a lot of important data analytical methods to look into brain imaging data, and there's quite some variance in the summer term. So 2 years ago, I think I only focused on this random field theory based stuff, and went a lot into the details there, more than we will do this term. Last year I did biophysical modeling and variational inference in the summer term, and this year I will do something that I haven't done for a number of years now, namely what you can refer to as multivariate analysis. In imaging, you often hear it under the label MVPA, which means something like multi-voxel pattern analysis. Or you can refer it to machine learning techniques. It's all essentially stuff that has been applied to neuroimaging data, which it hasn't really been tailored to neuroimaging data as much as this approach has been tailored and made specific to neuroimaging data. But it's things that you will come across. You already came across independent component analysis, and we will discuss the details of this in the summer term. It also features what some people, or what created a hype in like the last, let's say 5 years, namely neural networks. The old neural networks from the 50s and 80s came back in 2012 and were labeled. Where are neural networks called these days? Exactly, deep learning. So that came back as deep learning. And then there's also actually a somewhat weird combination of neural network approaches and what I'm particularly interested in, namely variation inference, and this is labeled variation autoencoders. So these are kind of, some people think, I think a little bit on vogue. Some people think it's actually very cool. I think it's on vogue, but the problem is it doesn't have to do much with biophysical modeling and really doing neurocognitive imaging. However, it's also something that you will see a lot, and that you also should critically assess, and should be able to critically assess for its neurobiological and neurocognitive contributions. So it's good that you learn about it. So that's the summer term. That's the content that we will go over. Now, what do you have to do to successfully complete the course? You will have to write or take part in an exam. And the thing is, there's only there's only one exam. This one exam has 30 questions, and each question gives you 1 point. And to pass the exam, you need half or more than half of the points. So you need 15 points or more. The questions you know as soon as you work through this script. And in addition to the questions, you also know the answers, because the question pool from which I will select 30 questions are these study questions in the script. Yeah? So there are these study questions which basically try to highlight the most important aspects of the stuff that I wrote before, and the stuff that will, the most important also in the sense that these kind of things will come up again. So they kind of focus your learning a little bit. There was, in the old days when I taught this course, I sometimes gave the question was sometimes give a verbose description, so a verbal description of something that was explained mathematically earlier, and then people were very confused what this is supposed to mean. So everybody wanted study question answers. So now there are study questions answers. Often these study question answers are just copy and paste from what the text says, essentially. It can be dealt with. What I will do, usually more towards when the exams actually happen, is because sometimes we discuss we don't discuss certain aspects, and then I usually take out the study questions that are related to the stuff that we didn't discuss here, so that the study questions really represent what we discussed or what I told you in class, and so that you feel kind of safe. So that's how the exam works. One can fail the exam, so that's actually usually like 1 or 2 people fail the exam. But if you study for the exam and essentially memorize all the answers to all the questions, then you are set, and you actually have learned a lot, I think. So that's, I keep asking people whether this actually works, and people are kind of happy with it. I mean, there's you have a lot of certainty in the way you will be assessed, but it's also not completely trivial to answer these questions if you haven't studied the material. And of course, the answers are a little bit shorter than the context, so you still need to study the material. These questions are often kind of knowledge oriented, or most of the time knowledge oriented. For some of the mathematical preliminaries, you also need to calculate little things, but these are more than calculations to make sure that you understood what's going on, and not calculations that are there to assess whether you can do some basic arithmetics. Yeah. So there's one exam and it has 30 questions. And in the old days, it was offered after the summer term, essentially the week after the summer term, and then the week before the winter term, so that you either study during the term and then take the exam, or you study during the term break and then take the exam. It turned out that this often led to the case that people didn't study anything until September next year, and then actually students proposed that you can take parts of the exam earlier, and we happily do that. So now there are basically many options how to take the exam, but always keep in mind there's only one exam, and you can only pass or fail this one exam. But you don't need to write the exam in 90 minutes after the summer term or before the beginning of the winter term next year, but you can already answer a subset of questions earlier. So the newest thing is that you can, before Christmas, answer the 10 questions on the mathematical preliminaries if you want. I recommend it, then you know the stuff, you know it by heart, and you can follow the material of the course much better. But you can also say, well, I want to go on a Christmas vacation and jingle bells and snow and so on. So you can also say, I only want to take the first 20 questions on the mathematical preliminaries and the GLM, so the stuff that we did in the winter term, after the winter term, or shortly before the summer term. If you do this, you will have answered 20 questions already by the beginning of the summer term, and then you have 10 questions left for the last third, and the last third is offered then on after the summer term and to the before the beginning of the winter term. What you cannot do is improve your marks in some way. Yeah, so I will actually not. No, that's not quite true, but I will. So it's only one exam, and you answer questions at different times. So if you, for example, take something here, and I actually get around to looking into the answers, and you will have like 6 points out of 10. You cannot try to improve your mark here for these 10 questions to get 8 points or something, and the same for the next 10 questions and in the third exam. Yeah, it's only one exam, and essentially you can view it as I will only mark this whole thing once I have the answers or not answers to 30 questions of you from you. Yeah, so there is no trying to improve the marks. If you haven't, if you fail the exam or you didn't partake or whatever, if you have less than 15 points by October 12th, then you have failed the module and you can retake the module in the next academic year, so 2020 and 21. Yeah, I think that's as much as I want to talk about exam right now. Other questions about the exam? No. Really, the exam is again here to help you, like the course is here to help you. It's basically for you to assess whether you got into this. Ask people from the years above you. I think it's for anyone who takes this seriously and who wants to learn the stuff, the exam is not the problem. So definitely not. Good. I think, yeah, that's a question.
Regarding Glm Based Fmri, does that include simple things like t-tests and ANOVA?
It includes, that's a good question, so it includes t-statistics. Simple, yes, it does, but we will not make ANOVA and t-test this explicit this year. This leads me actually to something else. So there are only 16 sessions in the winter term, and there are only 14 sessions in the summer term. So there's of course much more to learn about everything than we can cover in the course. And I basically, to keep me motivated teaching this course, I mix things up a little bit every year, so that but everything that I teach is important. It is. No, it really is. As you will see also in a second. There is much more, and I also have much more of material that you find on my website under this kind of mysterious label PMFN. Things, for example, like ANOVA in the GLM setting, and t-tests, f-tests, and so on, you find, which we will actually not cover this year. We also don't cover things like PPI, for example, or FIR this year, because we focus more on the covariance components than on the different design matrices you can have. You find this in this fundamental designs, and there you find a description of how t-tests, I mean, we will see how t-tests are implemented in the GLM, but we will, for example, this year not treat in detail, for example, 2x2 ANOVA with interaction or without interaction. For these kind of things, there are of course also YouTube playlists, so you can always go back to stuff that I taught in the past. So if there are things that interest you that are in PMFN that we don't cover this year, feel free to explore them from previous years.
I mostly ask this because I don't remember having read a paper that didn't report ANOVA results. I mean, FMI paper, that maybe include that many papers.
Sorry, what?
Because I usually, when I read cognitive neuroscience paper that reports FMI results, it's usually a simple ANOVA or t-test. But what we will learn are all these other things that I almost never see in papers.
I don't quite get the question. What?
I mean, when I see FMI results in journals or in papers, they usually report results of simple methods like t-tests or ANOVA.
So usually what they report is a t-test on the second level, and they will have done a first level analysis that involves things like restricted maximum likelihood estimation and covariance component estimation. And if they do the inference based on their one sample t-test, they will use some form of p-value correction, because otherwise they wouldn't get published. And this is either random field theory or some permutation method. And the random field theory is the stuff that is done by everyone who's doing SPM and FSL. One thing about papers is to say, they often will say we use SPM for statistical modeling. So where you wouldn't see that they use restricted maximum likelihood, this has to do with the fact that they don't know what they are doing. So, but that doesn't mean that we shouldn't teach and we shouldn't think about what people are actually doing. So they don't. So if anyone who uses SPM or FSL to analyze fMRI data, and this is just the standard, so you will find no one who extracts some imaging data and then does a t-test in SPSS on it, because people would ask, so what are you doing? Why are you not using some established software? If people are using SPM or FSL, they actually use fairly complex methods. But they will often not write about it because they don't know what they are doing.
Okay. But is it usual that researchers would use these complex methods and not report them, and report a simple measure like ANOVA or t-test?
I'm not quite sure what you mean by a simple method like ANOVA or t-test, because a t-test in fMRI is not a t-test like a t-test, because it's based on estimating a GLM with linear covariance components on the first level, and it's then based on evaluating the t-statistic with respect to a t-random field, which is something that in t-tests of like one sample or two sample t-tests that you are familiar from statistics, you never do, because you don't have spatially extending data. So yes, it's common that they don't know what they are doing, and it's common that they don't report everything that they should report. But yeah, if you go to my open science lectures on YouTube, you will also find something about the COBIDAS report and bits. And the COBIDAS report, for example, is a report, so you can look at that, is a report that gives some hints of how actually the results from fMRI studies should be reported. And if you know what you're doing, there would be many more things that you report. And of course, you would also report your code and share your code with people. Yeah. So yeah, I'm not quite sure of what kind of papers you're referring to. It may be the case that somebody so do these papers use SPM or FSL?
No, I mean, like also in psychology papers, like it's a simple design 2x2 ANOVA. These are the kinds of results I usually see in scientific papers, and not papers that report results of complex things that you might.
Yeah, but what kind of papers are you referring to?
What I read during the
sorry, what?
What I read during the psychology course in bachelor's degree.
Yeah, but sure, but this is now cognitive neuroscience and not psychology.
Yeah, but in biological psychology we also had to read some papers on that reported fMRI results immediately. But yeah. But
did they use FSL or SPM or some toolbox?
I never heard about them. But I might.
Can you send me one such paper, because it's my prediction error for this, or my surprise for these kind of statements is pretty large, because it's really not the case.
It just might be that because I don't know what it is, I might have just overlooked it.
I think that's actually the case. Good. Any other questions? Good, so none right now. Then I would suggest that we continue with actually getting started. So I think I've told you everything about the general course layout, exams, the material you have. One thing about the material, as I already mentioned, there are some sections in the script that are under revision, so they will be done in time for the given lecture. That just means that I have the material, but I want to work a little bit more on it to make it even better. So yeah, just yeah, bear with me there. It will you will in due course have the material, and you can also, of course, look into papers and stuff. And if you really feel you want to understand restricted maximum likelihood before we discuss it, then of course just Google it and go into it. Yeah. Good, I think that's about it. Well, any other questions regarding formalities, layout, anything? Yeah.
First, complete the same exams you said, but does it include the stuff that we're supposed to, like that we're going to review before, like the basis that you want us to?
The first exam, you mean?
Yeah, will that include questions in terms
yeah,
of
that's actually only questions from that. So the exam 3 parts. So the 3 parts of the exam, so 10, 10, and 10 questions, refer to 10 questions on the mathematical preliminaries, 10 questions on the GLM and for fMRI, and 10 questions on yeah, the summer term machine learning MVPA. Yeah.
It's the way you set up the
Yeah. Yeah, and as I said, so if you prefer that somebody's explaining mathematical preliminaries to you, there are the YouTube lectures, so you can also use them. But this material is really, really standard, and you will find many more YouTube lectures and millions of tutorials on the stuff that is in the mathematical preliminaries. Not so much on the stuff that is coming later, because that's more specific to what you are doing, namely cognitive neuroscience. Good. Any other questions? No. Good. So then let's get started. Today I want to actually go on without break. In the next couple of weeks we will then of course again have 45 minutes in a break, because that's, I think, healthy, at least for me. But today, because as a last remark, I'm also starting the other course today, so the statistics for data science, and that's in a new room, and I wanted to have a little bit of time before starting that, so that we don't start too late with this. So this is why we continue today straight away until 9:30. And of course everybody's also very much invited to the statistics for data science. That, I think you've seen the emails. I think I sent like 5 emails yesterday around to everyone who didn't run away, and everybody should have the information. Good. So then let's get started with statistical methods. So what I want to do today, and maybe also then beginning of the next session, is first to give you some general remarks on probabilistic modeling, so that you know what we are doing. It's not only probabilistic modeling, it's also modeling, data analysis, or however you want to call it in general. But for me, any kind of data analysis, if it's done sensibly in science, is probabilistic. But you can also do non-probabilistic analyses. They, for me, would be then analysis where you set certain probabilities to 1, and hence everything's deterministic. But yeah, so some general remarks on model-based data analysis. Then I want to show you what we do in this winter term in terms of how this looks in SPM data analysis, so that you get the feeling that the stuff that we will talk about in the winter term is actually real and important. And the last thing then is to get started on what the GLM is, GLM introduction, and I'm not quite sure we get really to this today, but let's see. So that's the plan. So this refers to, if you have the script, this refers to this introduction, and then we leave out all the mathematical preliminaries and then start in section 6 with a general linear model. So that's what it is in the script. So the general first thing to note, you can also call this data analysis. Are at least 2 fundamental aspects of data analysis. One thing, and that's kind of straightforward, but it's something that is usually, when you look into a data analytical method, not explicitly addressed, is that data analysis is always data reduction. Yeah? Or in in the worst case, it's actually a data reduction that keeps the amount of data the same. So then there's not much of a reduction. I haven't seen, or somebody would have to point me really to something where from the data, during data analysis, you create more data than there originally was, because that's kind of then you invent stuff in addition to the empirical data. But correct me if I'm wrong. So the typical starting point for any kind of data analysis is some data matrix where you have a lot of numbers. So you have numbers in there. And let's come up with some more random numbers here. You don't need to write down these numbers because they are just made up and have no meaning whatsoever. So you have some data that you might organize in a matrix where you have some columns. You can also in programming organize data in different ways. You don't need to organize it in programming in a matrix, but usually you can in the end think about the data that is being represented as being represented in a matrix. And you might have data and you have data in columns and rows that mean different things. So if you think about what we discussed in terms of fMRI data analysis, what would be something like a column or a row in fMRI data analysis once you have acquired the data? If you remember this slide with the participants and so on, so what would be the dimensions of the data for fMRI?
Activations and deactivations. Activations and deactivations of voxels.
Yeah, and I think what you mean is, in terms of the dimensions, when you say activations, you mean time. So you mean that something is happening over time, or at least I assume that. So remember that we had time here, and then we had the MR signal, and that was a time course of MR signal, and we had this for one voxel, and we had this for another voxel. Again, the MR signal for voxel 2 and so on. So remember the slide in the new cognitive methods section. So if we represent these data points in terms of a data matrix, we would assign the dimension of time to the columns and the dimension of voxels or space to the rows. You can also transpose this and have rows representing voxels and rows representing time and columns representing space. But usually data have these kind of at least two dimensions. I mean, another thing that you of course are very familiar with from undergrad psychology is that, for example, rows represent different participants, and the columns represent different conditions in which the participants took place. So in general, you have large data sets with at least two dimensions. And if you analyze these data, you will usually not report these data just as they are. I mean, you should, of course, share the data as they were acquired with your fellow researchers. So you should share your raw data once you acquired them, essentially. And definitely you should share them once you write a paper about these raw data and the analysis that you did, so that people can also work on the data that you acquired with public money, and also that people can try different analyses on these data and also, of course, reproduce your analysis. So you share these raw data, and you should, but it's not the only thing that you do. Yeah, so you don't just in a research project go to the scanner, acquire a data set, put it online after everybody agreed to do so, and then you go home. You could, I mean, it would also be a job, but what you usually do is you analyze the data, and this then results in different things. So, for example, for fMRI and for what we have here in GLM, you will find some brain activations. So that's the brain, and this is here a blob in the brain where there's some activation. And of course, if you think about fMRI data, if you look at this map, one dimension is missing here. So which dimension is missing? So if the original data had some resolution over space and time, and then you end up with this map, so what is missing? Time, exactly, because it's just an activity profile over space that somehow was created based on this spatiotemporal data. And hence you end up with essentially, if you want, if columns are time, you end up with one of these columns. Of course, this one column is not only one column that you randomly select from your data matrix, but it of course results and hopefully represents in a meaningful manner all the data variation that you have over time. But nevertheless, you have fewer single data points after data analysis than previously. So you summarize the data. You can also briefly say in this this data reduction aspect as this. So usually you have your raw data has many more individual data points than the summary that you report. And of course this also makes sense, but it's also a process that one should be aware of. And of course the summary depends on how you do the summary, and the result hence depends on how you do the data analysis. And this is of course important to make sense of the results. And that's kind of a ubiquitous feature of data analysis. Now, the somewhat, I think that's fairly clear, the somewhat maybe a little bit more surprising aspect of data analysis for you may or may not be the aspect that data analysis is always model-based. Even if certain people say we have a model-free technique, such as non-parametric statistics, or we're using ICA, which is model-free. Yeah, this just means that essentially you have a model that you don't want to talk about. So that's just essentially the big difference. If you want to talk about it, which makes a lot of sense, because after all it's your lens by which you assess data, then you see the model and you see that this is inherently your scientific method. So I think I don't want to draw this. It always looks horrible if I draw it. So I will open this figure. Maybe we actually use it from here. This is something that I have to present twice today, because it's so fundamental that also in data science we have to talk about it. Let's see what I can draw on it. No, that's not good. Then we look at it here, because here I can draw on it, I think. Yep. So this is science in a nutshell, which may surprise you, but that's how it is. Sorry. Once I get hello, good, that's better. So by science I mean natural science, quantitative natural science. I'm not saying that humanity is a bad thing. I'm just saying that natural science, quantitative natural science, works as shown here. So this is science, and outside of science there's reality, and reality we can only observe indirectly by terms of data in some sensors. Yeah? So this whole thing is quite, of course, inspired by cognition and cognitive neuroscience, where, of course, you cannot assess the outside world directly, but what you can assess as a cognitive system are the effects that aspects of reality have in your sensorium. Yeah, so you don't see or you don't interpret something in the outside world directly, but what you're dealing with is the activation pattern in your retina or in your somatosensory sensorium or in your auditory sensorium. Yeah, so that's the fundamental idea. It actually means, kind of more philosophically, that there's actually some belief that there's an outside world, which is hard to prove, but it's actually not, one cannot prove that there's an outside world or show or find evidence for that, but common sense says there is an outside world, but then common sense also says that, okay, there's energy in the outside world, the sun shines and light is reflected from components in the outside world, and these then give rise to activation patterns in our sensorium, and the nervous system is dealing with these activation patterns. And the same thing goes for then the scientific method. So if we acquire data on a brain imaging scanner, the data that we acquire exists in the reception coil as some electrical activity, which then corresponds to some activation in an extended sensorium. So you can view kind of neuroscientific methods or any kind of measurement techniques as an additional sensor that humans have built into their entire setup, so that they can sense, for example, these electromagnetic waves. Of course, they don't sense them in a perception sense, but they can record them and make sense of them. The important thing is that this means that data is also, of course, part of the scientific method. Data is not kind of the objective thing that holds the truth, because the way you set up your sensors, of course, determines what kind of aspects of reality you're sensitive to. So, and then somehow a sense is made of these data. The question is whether it needs to be made, but I guess it needs to be made in terms of cognition if for some reason this cognitive system wants to recreate, so survive and recreate, which seems to be fundamental aspect of things, or at least living things. And the way this can be described is here shown in terms of model formulation, model estimation, and model evaluation. So the basic idea is that any data analysis can be captured in terms of a mathematical model that is that can be formulated, written down, and thought about, and also simulated on a computer, which allows to predict data. And the model that we will deal with in the winter term very explicitly is the general linear model, which mathematically takes this form. And what this means, we of course will discuss once we start working on the general linear model. So we can write down a model for data. Of course, what we need to specify when we write down a model is what these different model components actually mean. Now there's a y, there's an x, there's a beta, there's an epsilon, and we need to say what these symbols are meant to represent. Yeah? For example, in the GLM, the y, if we are talking about fMRI data analysis, will represent the time series data MR signal from a single voxel. But we will get back to that. Then a fundamental aspect of data analysis, science, however you want to call it, is to adapt the model in light of the data. And typically this is referred to as parameter fitting in introductory courses. So your model commonly makes fairly general predictions so that it is able to make predictions for many forms of data. And given some data, you want to know how specific parts of the models have to be set to predict your current data set. And this is what is known as model estimation, or as parameter fitting, or as statistical inference. So there are a number of terms for that. And this is important because it can be done in different ways, and of course also determines a lot how the data that you observe and the model that you have about these data then give rise to some interpretation. What I forgot to say is that the model that you formulate, you can also call your theory. You can also call it your hypothesis. When we talk about hypothesis testing, we will be much more specific about what a hypothesis is, but for the moment, a model can also call it theory or hypothesis. In terms of model estimation, what we will discuss is how, for example, maximum likelihood estimates arise in or are evaluated in GLMs. So this is an example for a better parameter estimate that then directly gives rise to these blobs that you always see if it's related to the variance estimate. So that's another fundamental aspect. And then usually you have estimated some parameters based on your model, and then you can do different things. So one thing that you can do is to ask, for example, how the way it's done in brain imaging, if you assume that there is no activation anywhere in the brain and everything that you observe is just due to some smooth variation in space of the activations, but without any non-zero component, then you can, for example, ask whether there's enough evidence in the ratio of your beta parameters and your variance parameters, what this means in detail we will see, to reject some null hypothesis. So for example, p-values that you are familiar with for model parameters is a typical form of model evaluation. Another form of model evaluation are f-tests, which go into the direction of model comparison. So I guess you've seen ANOVA with f-tests. And this is model comparison. Another thing that people like to do these days is Bayesian model comparison, where you look at the marginal probability of the data to compare different models in their ability to explain data. And then, based on this evaluation, you make a statement. You say, okay, when we look at these data from this perspective of our model, we can summarize these data and ascribe this and this meaning to this data. And then, of course, you don't go home and say, okay, science is solved, let's finish that, and I don't know, what would we do instead? I don't know what I would do instead. No, well, kind of. Oh, make music. So we've done with science, so let's make music. What you usually do is, and also what your peers tell you is that, yeah, that's quite good, your model, but can't you do something better? And then the idea would be to go back to the model formulation step and rethink of how you can, for example, get rid of certain assumptions in your hypothesis, your theory, or make your model even more specific to the kind of data that you have by putting in more assumptions. So all sorts of things then go back into the model formulation stage. And this is actually something that we will not rigorously explore. Actually, this kind of reformulating models. So we will be happy by going through this process here once for the GLM, and then later on for the multivoxel pattern analysis. In a way, you can see actually when we discuss, so whenever we discuss a new data analytical method, you can see this as a way of going back to the model formulation stage by basically abandon your previous model and come up with something completely different. Yeah. Questions about this philosophical kind of view of data analysis, or objections or remarks? Have you seen this before? Who has seen this before? Good. And also in physics, people agree with this, that data is part of science?
I would say so.
Good. Yeah, but physicists also somehow believe that here in the outside world, sometimes we have physicists that believe that something like this is happening. That, didn't we hear this last week, that mathematics is the language of nature? Yeah, but that's wrong. Mathematics is the language of humans talking about nature. That's not. Yeah.
Physicists also say that.
Okay, that's good. So then you know the right physicists, because some physicists are a little bit confused there. Good. So this is kind of the overarching way to view what we are doing, and I will point out when we discuss the GLM at which stage we currently are. And you should also, and this is one reason why I introduced this in the first place, is that when I studied data analytical methods, sometimes in, oh interesting, this E should be large, small. Sometimes in, if you read about data analytical methods, it's people don't distinguish these aspects clearly. So then it gets really hard to understand what people are doing. So if they kind of portray what they are doing and can't differentiate between the model that they're formulating and the parameters, estimation technique they use and so on, then already you should be very suspicious. And if it's confusing, if they can't say, this is my model. Now I have different ways to estimate the parameters of the model. This is how I do that. And then now I have parameter estimates of my model. So what do I do with them? If people can't say, give you answers to these kind of very basic 3 steps, then there's a good indication that they don't really know what they're doing. Because they, because as soon as you think about what's actually happening, you want to disentangle these things, because it doesn't make, so parameter estimation techniques you can combine in arbitrary ways essentially with different models. So you don't need to use maximum likelihood for parameter estimation. You can use Bayesian approaches to parameter estimation, and you can combine, for example, maximum likelihood estimates or Bayesian estimates with different kinds of models. So this is all mutually what do I want to say? Mutually not exclusive, independent. Independent, yeah. So you can combine parameter estimation techniques with different models, and for a given model, it's not predetermined that you could or should use a certain parameter estimation technique. So people should really, if you don't understand how somebody analyzes their data, ask them, so what is the model that you use to model the data, and how did you estimate the parameters, and how do you then make sense of this? If they can't answer this, then just tell them, you should get out of science quickly. Or, that's the other option, visit Dirk's lectures, and then you know what's going to happen. Good. So to make this then, from this very abstract level, make this quite concrete in terms of fMRI data analysis, I now want to show you these steps in SPM if there are no further questions right now. Because I want to continue our little example that we started last week in neurocognitive methods. and show you basically the last part of the data analysis that for fMRI data that we started or introduced last week, where we did a lot of pre-processing and ended up with these normalized data. If you remember that, so we, let me add SPM first. So we looked into this data from the checkerboard experiment, where checkerboards were presented at 2 different contrast levels to 1 human participant during 1 run in the fMRI scanner. And what we looked at on Friday was the pre-processing, data pre-processing. And you might remember that there are these different files. So do you remember what each of these files encodes, or what is in this file? So these files, and then these files that have different prefixes. So do you remember what this is? You were all there. And then you went drinking on the weekend, wiped clean, everything. So does no one remember what these files are? Oh, you must remember what these files are. Come on, try it. It can only be wrong and nothing bad will happen. So what is in this file? Come on, please, someone, you were there. And you can watch the YouTube video again. Maybe you should watch the YouTube video on, so you all have headphones as I do, so just turn it on. So you really, no one remembers what's in these files, so have guesses. What could be in these files? Are there kangaroos in these files? Yes or no? No, no kangaroos. Good. What else could be in these files? Could it be the stimulus? Do these files, if you open them and look at them, do you see checkerboards? Yes? Okay, no, you don't see checkerboards. That's wrong, sorry. Actually, we looked at what the checkerboards are, and so these were these onsets, and you might remember that there were 2 onset functions, which are just the time points when a stimulus was presented. So these are kind of the checkerboards. But what is in these files, please?
I wasn't there, but they might be the repeated measures.
Yeah, and what if we visualize one of these files, what do we see?
I wasn't there.
Yeah, but what should it be? It's fMRI data. I mean, come on. Is it a picture of the foot of the participant? So what might it be? Come on. It cannot be that you forgot this. Anyway, apparently you forgot it. So these files are, of course, the volumes that were acquired, so the 3D pictures of the brains. But yeah, we did this, really. Please, so the way my courses actually work is that I assume that in the next session you know everything from all sessions before, because it's kind of hierarchical. And if you don't remember the things, then you will be lost fairly quickly. So please prepare for the next session by going over the material from the last session and memorize things. I mean, this is actually not something that is part of the exam, so you could argue, but we don't need it for the exam. But this is something, I mean, what else should it be? So this is one of these files, and I hope at least your visual memory works. And do you remember seeing something like this? Good. So these are the EPI volumes, and these are the smooth EPI volumes, and there are 441. So it's a long time series of these 3D data sets, and each of these points that you see in there is a voxel. Now, what we want to do is do a GLM analysis of this, because this is what we will discuss in terms of the in the winter term now for quite some time. And there are these 3 steps of model formulation, model estimation, and model evaluation involved. And the first thing that we will do is model formulation. This, now you should pay attention, in terms of model formulation, this means that you specify a general linear model, and this means in terms of fMRI data that you specify the onset functions of your stimuli, because the fundamental aim is to basically tie together your experimental paradigm, and so that happened while people were measured, and the measurements. Yeah? We will go over the process that I'm showing you again once we know a little bit more about the GLM, but for demonstration purposes and for the fact that you also see what we discuss in the winter term means in real life, I'm showing you this right now already. So we now formulate the model, and the important thing is that during model formulation we bring together the experimental paradigm, and our model. What we also do, and this is maybe a little bit surprising and also doesn't need to be done like this, is that during model formulation we already also tell, in this case, the data analysis pipeline, what kind of data we want to analyze. Really, putting in the data is only part of model estimation, but to do model estimation, SPM needs to know which data we're working with already. Another way to see is that, of course, during model formulation, you formulate a model for a specific data set. So in this way, it's also part of model formulation. So now we want to specify a GLM model. So what we will discuss in detail over the course of the winter term. And for the analysis, we essentially need to tell SPM in this case where we want to save our data. Because we're dealing with temporal data, we have to tell SPM in what kind of temporal resolution our data works, and what the stimulus onset functions refer to. In our case, these were seconds. Then we need to specify what the TR was. So what was the TR? Remember what, actually 1.5? Yes. Remember the term TR from last week? So what is TR?
Repetition time.
Yeah, it's the repetition time. And what does it measure? Yeah, so it's the time between 2 excitation pulses, and because this is EPI data, 1 excitation pulse refers to the acquisition of one entire 3D volume. So this is basically the sampling unit of the data. So each of these volumes that you see here, or these 441 volumes or 3D images of the brain, was acquired over the time of 1.5 seconds. So we have, as temporal resolution of the data, we have this 1.5 seconds. These things we don't have to worry about right now. What we need to specify is the data we want to analyze. So this, for this we are interested in our smoothed and normalized data. So that would be this. No, that would be too many. Why do I have 2 of them? Because let's briefly, did it go away here? Because we did this, we have different forms of things there, so that was better. So These are the 441 measurements that were made one after the other and recorded by the scanner. And then we had two conditions, namely high contrast and low contrast. I'm not quite sure actually which one is now the first one. Let's say the first onsets are, let's say these are the low contrast, maybe the high contrast. We would be able to tell that from the data, and of course this should be, if this would be for real, this would be documented. So we're telling when the experimental manipulations happened, and yeah, we need to specify how long each stimulus took. And something that we will discuss later is that it makes sense in event-related designs to use 0. So you can see we can now already specify the data, but we have one more condition. Let's do it like this, and then overwrite things. So the other thing is the high contrast checkerboard. So remember, hopefully. And for this we take the other onsets. And let me just do one thing instead of everything, in case that everything goes horribly wrong, that I don't overwrite the results that are already in these folders, so that we will have something to look at in the end. So let's change where we want to write this. So model formulation. This is all we need to specify to formulate the model, and then we can click go, and then it does its model formulation, which takes a little bit of time. Maybe we should also turn off our So now it has formulated the model, and what you can see here is the design matrix that we are using. And what this means we will of course discuss. But the design matrix is the fundamental model that we use to actually analyze the data of each voxel. So this design matrix that you see here is the design matrix for the time series of each voxel, and you see the time series of each voxel represented here. So here are the different images that correspond to the rows of this design matrix. Today the aim is not so much that you really understand what you see here, but that you get a first exposition to this, so that you're exposed to this, and that you believe me that when we talk about design matrices later on, that this is something important because you have seen this in SPM. So yeah, don't if you feel completely lost, that's fine, but there is a design matrix that you have seen now. Now this is the model formulation aspect. Now we don't have any results yet, so the next thing that we need to do is to estimate this model. And this is what we will do next. So we have now here fMRI model specification or model formulation. We have done that. And the next thing now is that we want to estimate this model. And this is what we will do once SPM comes up again. So you don't have to close SPM in between, I just do it so that we don't that I don't get any problems. So to estimate this model, there's a button called Estimate. Makes some sense. And the model is now formulated in terms thought it would be in here. It's not. So for whatever reasons, it's formulated in terms of this spm.mat file, and the only thing that we need to specify if we want to estimate it is the model that we actually want to estimate, and then click Go, and it will estimate the model. So what we're using here, and what you can read here, is that model parameters are estimated using restricted maximum likelihood, since our focus on restricted maximum likelihood in addition to maximum likelihood. There is something about AR1, so autoregressive errors, and this is what we will also discuss. Now, in terms of the practical aspect, we click Run, and then it starts with a problem. So let's see what the problem is. The problem might be that the files are actually named differently. So I wonder why this actually didn't save our thing here. Where did it save it? Let's do maybe let's not do it. So ideally it would run now, and you have seen that there is some restricted maximum likelihood. The reason it doesn't run right now is that this SPM-MUD, which I just wanted to basically run now, has hard-coded in it different file names than the ones that are actually on the website, in the Google Drive folder, sorry. But there is already an estimated version here which we can look at. So during the estimation you also don't see much. You can look at some older videos where the estimation is running. You just see that it says REML is doing something, and then in the end it says estimation is done. So that was model estimation with the additional practical highlight that something didn't work, which of course in practice is always the case. So it didn't save our original SPM. And then model evaluation. That means in terms of SPM, looking at the results. And let's hope that this works. So in terms of the results, what one typically looks at in GLMs is parameter contrast. So this is again this subtraction approach that we discussed last week and that also Rainer Göbel mentioned. These parameter contrasts look like this. They are actually referring to contrast weights on the beta parameters. What this means we will see. Then one can answer certain questions. The one thing that is kicking in here already is the notion of random field theory based p-value evaluation, where the first question is how high you want to set the threshold, what is referred to in brain imaging as the cluster forming threshold, that determines the probability of observing activations under null model. And the one recommendation is to set the threshold corresponding to a p-value of 0.001. So it needs to be relatively high, because the old results by Robert Artner from 1980, which were then introduced to the neuroimaging literature by Keith Worsley early 90s, and also Carl Friston in the early to mid 90s, they all work for random fields in the limit of high excursion set thresholds. What this means we will see, but this is basically what's kicking in here. And then you can also give it for the set level and cluster level, you can give it an extent threshold. We keep this as 0. And then if things work, we observe this. So this is now the model evaluation part in a typical fMRI analysis. You see that there are activations here in what's called a glass brain. So I will show you a nicer visualization in a second. So this is basically 3D views of the brain, and you see some activation primarily in right visual cortex. Because these checkerboards were presented on the left side. Remember, we looked at the ERPs as well. And you get the p-values corresponding to these clusters that you see in there. Yeah. So you have here some p-values, family-wise error-corrected. So you have, first of course, you have a T-map here. So that's a T-map. And with the T-map, you get different forms of inference p-values. So you get family-wise corrected at the peak level, family-wise corrected at the cluster level, and you get a set-level p-value. What these things mean, I just, as you of course know, wrote a long paper about, and we will discuss that at the end of the winter term. So that's this random field theory-based inference, which is in this table. And of course, you can say we did a t-test. So if you write a paper, you say we did a t-test because this is a t-value and this is our t-value and our p-value is smaller than 0.001. Yes, you did, but what you actually evaluate these t-values against are t-random fields, and looking at the specific features of these t-random fields, namely the maxima and the cluster extent. Now to look at this, yep.
I didn't get that. Why do we have so many p-values, like for each?
Okay, yeah, that's also a good question. So the p-values that are shown here are for local maxima that are about 8, it says local maxima more than 8 millimeter apart. So each p-value refers primarily to each cluster. And then if there are multiple maxima per cluster, then it shows you 2 additional within this cluster of local maxima. But you can actually change that. So if you want more fine-grained, you can change these 8 millimeters. One thing that's actually interesting is that ideally, or what this shows in a way, is that our initial screening threshold was a little bit too low, because this whole random field theory business is based on the assumption that there are only that each cluster actually has one local maximum, and so we could that basically the number of local maximum, the number of cluster is the same thing, but this is here not the case, so we could use a higher screening threshold if we wanted to. But we will go into this by the end of the term in some depth, because this is model evaluation, so it's for the end. And to show you this a little bit nicer and the typical way that things are usually portrayed, you can of course overlay this t-value map on a single participant brain, and then render and then display these kind of gray values here using yellow colors, and then you see these typical activations. Yeah. So this was model formulation, model estimation, and model evaluation for fMRI data from a practical perspective. Yeah. But as you might also notice from a practical perspective, one can do that and then one gets the results. But just from doing this, from clicking this here in this software, you don't know what you're doing. Yeah. Or if you now already think you understand all of this, good, or maybe not, no, actually not good. So that would be weird if you go away from today and say, oh, now I understand it. Then I don't think the contributions you will make to cognitive neuroscience are really that valid, I would think. So if you feel, but you have now seen that these things happen, and I will always be able to refer back to that. So that's actually all I wanted to do today. Are there questions right now? No, if there are none, then we stop here and continue next week with the introduction to the GLM. So please read this introduction aspect and also read then chapter 6 on the GLM and work on the mathematical preliminaries. Good, then see you either next week or in a couple of minutes, depending on what